Okay, so for the angular momentum, we can write it as is I is equal to I omega, and that's going to be written as I alpha t. And we like this here. If we look here, the alpha, which is going to be change in omega over change in time, which is going to be the change here is 10 spokes per second over 5 seconds, which makes it 2 spokes per second squared, and that's a constant change in angular acceleration. So we're gonna model as a straight linear linear line, but when we introduce side seconds, the block falls, so then there's no tension that's gonna cause any angular acceleration. So it's gonna be flying out like this, and then the torque is gonna be equal to I alpha, and we know alpha in this case is constant, so for the first 5 seconds it will be a horizontal line right here like this, but then after 5 seconds, when there's no more when the block is not creating any tension, it's not going to be accelerating anymore, so it's going to be moving at a constant omega, so it will be modeled like this. And then for Ke rod, we know Ke of it, which will be in this case Ke rod, is 1/2 I omega squared, and we can rewrite that as 1/2 I alpha squared t squared, because omega is equal to alpha times t, because it's constant angular acceleration. And so this is going to be a parabola, so it's going to look, because then it's t squared, so this k versus t is going to start as a parabola, but then once it reaches 5 seconds, so once it reaches the 5-second mark, it's going to flatten out and it's going to become like this, because then after that alpha is going to be equal to 0 and it's going to be moving at constant. Okay, so for linear momentum with the block, it would be modeled as P as momentum equals mass of the block times velocity, and we can rewrite that as m times at. And in this case, it's going to be for the first 5 seconds, because it's a constant tension during the first 5 seconds. It's going to be moving down. It's going to be accelerating downwards at a constant acceleration. But what we have to first say is that first 5 seconds, I can model as A, which we'll find later. It's going to be less than G, because then there's a tension, because there's the tension from this string that's pulling against it, and gravity is going to is trying to pull it downwards while it's pulling upwards. So this acceleration, which is the net during first 5 seconds, to be less than G, and so that'll be used for later on for this other graphs. So then if we model like this, it will be first MAT for the first 5 seconds, so it will be a linear line like this. But once it reaches 5 seconds, it will be modeled by MGT, because velocity is changing by acceleration to gravity, because there's no more tension from the string, because it's ran out, because then it's not attached to the block anymore, or I mean the wheel, so then it's gonna become a steeper slope. And then for the next part, for U, we know I'm gonna set it up, so B, so U in this case is equal to MGH, and then this H we're gonna write as HI, which we don't know what it is, and it's gonna be equal to minus the change in height. So then we can model change in height as VIT, which in this case is VI0. So it's minus A over 2 t squared, because in the first 5 seconds it will be modeled by A over 2 t squared. But then the change in H after that, it's gonna be modeled by GT squared. It's gonna be different, because now it's gonna be modeled by GT squared. So we're gonna say it's minus G over 2 t squared, and then but there's going to be a velocity here during after 5 seconds, because it's going to be moving during that. So when we model it, our U is going to be equal to mg times hi minus a over 2t squared, which will cause it to be a concave down parabola, so it'll look like this. But then when we notice that after 5 seconds, because now there's more tension, but we said earlier, G is going to be greater than A, the acceleration of gravity is greater than the initial acceleration, so it's going to be still concave down, but it's going to be going down steeper and steeper. It'll be the magnitude of concavity will be greater than the previous one. And then for the K kinetic energy graphs, we could rewrite it as, so it will be K linear in this case is equal to 1/2 mv squared. And so for this one, this velocity is going to represent the hanging masses. So that we already have our graph for the KV graph. So it'll just be a regular concave parabola but the concavity does not change and there's no sharp points in it throughout the whole entire as V changes. But then when we look at this one, this is a KT graph, so instead of V, it'll be T. So now we can rewrite this as 1/2 M, and since it's a constant acceleration of A during the first 5 seconds, it'll be modified AT squared. And then, but if you contrast it to the other one, so it's K linear after the first 5 seconds. After 5 seconds, it will be 1/2 M, and since the acceleration of gravity is just G, it's just the acceleration of gravity, we say it's GT squared. And then we could start drafting it, so it's going to be similar to this, but it's going to be flipped upside down, so it's going to be concave up initially. It'll look something like this. But then after 5 seconds, since acceleration of gravity is magnitude is greater than A, it's going to be shooting straight. It'll be a sharp point, and it'll be going up at increasing at the concavity will be magnitude of concavity greater, so it'll be increasing. So the change in velocities will be greater each increment of time. And to fix the previous mistakes, this is going to have an arrow here, arrow here, arrow for the PT graph, and arrow in KV, because we don't know when the block is going to land, and so we're going to put an arrow there just because we're assuming it's going to continue falling for who knows how long. C, we're finding angular velocity. So if we look on the graph here, at t equals 5 seconds, it's currently at 10 spokes per second. So then we say omega at t equals 5 is 10 spokes a second. And we know that the wheel, to make a full entire revolution, it needs to go through 16 spokes. So it'll be 16 spokes to cover 2 pi rad, which in this is equal to 1 rev. And if we simplify this, we do 1 spoke, so we divide both sides by 16. 1 spoke is equal to 2 pi over 16 rads, or is pi over 8 rads per spoke. So now we could just multiply it over here. So to get it, we multiply it by the 10 spokes per second. To cancel out spokes, I have to multiply it by its rads per spoke. So we pi over 8 rads over 1 spoke, which cancels out. And then once you simplify this, you get approximately 3.927 rads per second. And in the graph, in the diagram shown, it's going to counterclockwise motion because it's pulling it down here. So then it's going to be accelerating towards, it'll be accelerating, and it would just be rotating like this, which is counterclockwise. Okay, for part D, so I'm going to set up alpha is equal to change in omega over change in time. So alpha in this case, I'm going to take the omega at t equals 5 minus omega at t equals 0 all over the change in time, which is 5 minus 0. And we just this clear earlier that the omega t equals 5 is 3.927 rads per second. And then I can take the magnitude here, and then we divide it by the amount of seconds 5, because then 5 minus 0 is 0, and initially it's at rest. So now the magnitude of our acceleration, our angular acceleration, is 0.785 rads second squared. Okay, so part E, to find tension, first I'm going to convert this alpha into acceleration. So we know that acceleration in this case is equal to alpha times the radius. And what we know is that the radius here, I'll put this capital R because that's what it said, is 30 centimeters. So it's going to be our 0.785 rads per second squared times 30 centimeters, which is 0.3 meters. And in this case, our acceleration is about 0.236 meters a second squared, and that's in magnitude. And then so I'm going to set a net force of the block of M, which is going to represent the block here, is equal to small m times a. Well, I'm going to put this a sys, or a block in this case. This will be a block as well. And then in this case, there's two forces here. So there's the tension and the gravity. And in this case, the gravity will be the one that's greater because it's pulling it down, because the block is descending. So it'll be mg, which represents the force of gravity, minus t is equal to ma block. And then I can isolate. So if I subtract by mg and then multiply both sides by -1, I get t is equal to mg minus ma block. And then I can start plugging numbers in. So t is equal to the mass of the block, which is 50 grams or 0.05 kg times 9.8 minus the mass again times our acceleration of area was 0.236 meters per second squared. And so our tension in this case will just be equal to 0.478 newtons, and that will be the tension of the string. Okay, so now for the net torque. So net torque in this case is equal to F perpendicular times the radius. And we know the F perpendicular in this diagram. So we take it right here. So I'll say this is R, and this here is the tension. So now our F perpendicular is going to be T of the string. So net torque is equal to T times R. And in this case, if we simplify it, it will be, we got earlier, so it will be 0.478 newtons times the radius, which is 0.3 meters or 30 centimeters. And in this case, the net torque will be 0.143 newton meters. And we look at the line of how it's rotating counterclockwise motion, and it's the rest. So then it will be, the torque in this case will be 0.43 newton meters, and this will be in counterclockwise, because that's the direction this because it's the angular acceleration is in a counterclockwise motion. We're looking at, if we're trying to find a moment inertia system, so I'm going to set a net torque again, which we found earlier is 0.143 newton meters. And then now we go, instead of writing as F perpendicular times R, I'm going to write as I system times alpha equal to our net torque we found earlier. And then we could isolate I system by dividing both sides by alpha. So it'll be 0.143 all over alpha. And then we could start putting our numbers. So I system is equal to our 0.143 divided by our alpha, which we declared earlier as 0.75 meters per second squared. And then our moment inertia of the whole system is going to be 0.183 kg/m squared, and that'll be our moment inertia of the whole entire system in this diagram. Just find the mass of this, find the value of m. I'm going to set up the moment inertia I system, and now we have to find what it's made of. So we know here that there's 16 spokes. Each spoke has a moment inertia of its mass m over 48 times the length of the spoke, which is in this case is 30 centimeters, and that's all over 3. And then we have to multiply by 60 because there's 60 of them. So we're going to set up 16 times m over 48 times r squared all over 3, and that'll be the total moment inertia of the spokes. And then we got to factor in the rim here, and so the moment inertia of this is supposed to be mr squared, because it's a hollow ring, and we're assuming it's thin, so it's going to be, its c value will be 1, so the moment inertia of that will be mr squared. And now we can start simplifying it. So 16 over 48 is 3, is 1/3, and then 1/3 times 1/3 is a 9. So I'm going to write I system is equal to mr squared over 9 plus mr squared. And then I'm going to isolate for it. So I'm going to divide I'm gonna isolate for m, so I system is equal to m times r squared over 9 plus r squared. And then I'm gonna isolate for m, so I system is equal to over r squared over 9 plus r squared, and focus, is equal to just m. And then we can start plugging them in. So m is equal to what we got earlier for our moment inertia of the system, which is 0.183. And that's going to be divided by 0.3 squared over 9 plus 0.3 squared. And when you simplify that, you're going to get about 0.0388 kilograms. And if you convert it into grams, multiply by 10 to the power 3 grams over kg, you get approximately 38 grams as the mass, as that's the value for m. So it'll be 38 grams as your answer. Alright, first I'm gonna prep to find the omega at t equals 3 and the velocity at t equals 3 of the hanging mass. So if you look here, it's gonna be at t equals 3, it's gonna be 6 spokes per second. So omega at t equals 3 is equal to 6 spokes a second. But I want to convert that into rads, so I'm going to multiply by what we did earlier, which was multiply by pi over 8. 8 rads over spoke is 1 spoke, so this cancels out. And now once we simplify that, we'll get an omega at t equals 3 of 2.356 rads a second. And I'm just looking at the speed for now, or the magnitude of it. And then if we're converting it to v for the hanging mass, since I'm gonna multiply. So in this case, v at t equals 3 is equal to omega at t equals 3 times the radius, and we know we found earlier is 2.356 times 0.3 meters, because velocity is going to be equal to omega times r. And so when we get that, it simplifies down to about 0.706 meters a second. For the KE of the system, it will be much simpler now because we have all our values. So we have KE linear at t equals 3 at the block, plus the KE rod of the wheel at t equals 3. So I can expand this as 1/2 times mass of the hanging mass times v of t equals 3 seconds square of the block, plus 1/2 times I system times omega at t equals 3 seconds squared of the wheel. And now we can expand. Now we can start plugging in numbers. So 1/2 times 0.05 kilograms times v at t equals 3, which was 0.706 meters per second squared, plus 1/2 times our moment inertia was 0.183 multiplied by 2.356 meters per second squared. And so now our KE system is going to be equal to approximately 0.520 joules. And so that will be the KE of the system at t equals 3. So let me fix this. It's at t equals 3, and it's at, so this KE system is at t equals 3 as well. At t equals 3 seconds. Meter. And so that will be, this will be our KE the system at t for J. I'm going to set up the tension. So we found earlier, and of our tension is going to be equal to the mass of the block, my hanging block minus mass times gravity minus mass times the acceleration. This case will be output as T1, and so T1 is equal to 0.07 in this case now, because that's a new mass. Multiplied by G is 9.8. minus 0.07, and we're assuming that's the same system, it's similar, not same system, I mean the same graph, so the alpha, so the acceleration will be the same, so it'll be 0.234, and now result in the new tension is 0.67 newtons. Now in the new tension of the hanging mass here, of the 70 grams, and then for to set up this one mass, we're gonna do net force of F m nu is equal to m nu times a, and in this case we know that our two forces here, so in this case we're assuming it's going to continue rotating counterclockwise and accelerating this acceleration, so that means here the tension is going to be greater than the force of gravity, so like this can follow it up and continue rotating counterclockwise, so it will be T2 minus m nu times g is equal to m nu times a, and then we just isolate for T2, so that will be equal to m nu g plus m nu times a, and then we're going to set up net torque. So net torque is going to be is equal to F perpendicular times R, and in this case it was 0.143 because we're assuming it's going to be the same, is equal to T1 R, because T1 is going in counterclockwise, and that's going to be the greater one, so we're taking out counterclockwise our line of motion, minus T2 R, which is trying to rotate in a clockwise motion. And then I notice here that they both have R, so I divide both sides by R, so you have 0.143 over R is equal to T1 minus T2, and then I'm going to isolate for T2, so I'm going to subtract both sides by T1, so it'll be 0.43 minus over R minus T1 is equal to negative T2, and then I'm gonna flip the negative sign, so this will become positive. This is positive and negative, so now T2 is equal to T1 minus 0.143 over R. I can expand T2, so it'll be T1 minus 0.143 over R is equal to what we found earlier, so it'll be m nu g, and I'm going to simplify this, so they both have m nu in here, so I could put it as a coefficient for both of them, so m nu times g plus a, and then I just divide both sides by g plus a, so then we have m nu is equal to T1 minus 0.143 over R, this thing is all over g plus a, and now we start plugging numbers in. So our T1 is 0.67 minus 0.143 over 0.3 all over g, which is 9.8, and then it will be plus our 0.234 will be found earlier, and then our m nu now will become about approximately 0.0193 kg, but we multiply 10 power 3, so it'll be 10 power 3 grams over kilograms. Our new mass will be about 19.3 grams, which will be the new mass of the other case. So we write T1 is equal to m times g minus ma, because that's the tension in the left string, and so we know we can simplify this as T1 is equal to m times g minus a. And what we know in this is the tension. This is how you model the tension for both systems in the left string. So this will be put this as m1, and then the other one, T1 prime, is equal to m1 prime times g minus a, and so this was 0.070 grams and this is 50 grams. So in both systems, since the omega graphs is the same in both, if the omega graphs are the same, that in the first 5 seconds, that means it's gonna have a is going to be angular acceleration is going to be the same, and angular acceleration is the same, and the radius, so we're using the same wheel with the same spokes, and the radius is the same. That means the acceleration of the blocks will be the same in magnitude. So in this case, if we look at here, since they both have g minus a, we just compare their masses. And the first one has a mass of 0.05 kilograms times g minus a, and the other one was a 0.07 times g minus a. And since this is bigger, 0.07 is bigger than 0.05, that means the tension in left string increased when it became a 70-gram block instead of 50 grams.